Hi, in this video we are going to talk about GANs or Generative Adversarial Networks. So these architectures are like the core of this whole course series. From now onwards we are going to talk about different variants of GAN, their benefits, their limitations, etc. But now let's see the general idea of GANs. It was first invented in 2014 by Ian Goodfellow, and these are implicit density models. And what do I mean by implicit density model is that these models don't learn about data distribution. So if you go to previous videos where we have discussed variational autoencoders and standard autoencoders, you have observed one thing, and that is, first of all, we have to pass our image from the encoder, and then we need to pass that latent space from the decoder. So basically that latent space is being learned by the encoder. Those architectures were not implicit density models, they were all explicit density models. They were learning about the data distribution. But in case of GANs, we are not learning about the data distribution. There is no encoder and decoder in generative adversarial networks. We are going to give some random noise to the generator, and then generator is going to generate a complex distribution of that noise. So that's why GANs are implicit density models, and variational autoencoders and standard autoencoders are explicit density models. There are two parts of GANs. One is called the generator and other one is called the discriminator. So generator is like decoder, which is going to generate the image from a noise, and discriminator is going to discriminate between two different things, as the name suggests. But in the upcoming slides we will see more about discriminator. So generator tries to generate new images as discussed, and discriminator tries to differentiate between a real and generated image, or real and fake image. And in this architecture, the generator and discriminator is going to compete with each other, because generator will try its best to produce as much realistic image as he can, and discriminator is going to discriminate between real and fake image as best as he can. That's why there is word adversarial in the generative adversarial networks. Now let's talk about the general architecture. Obviously at a first look you will get confused, there is a lot going on, but let's see step by step. First of all, we are going to give some random noise to this model. So this is our whole GAN, generative adversarial network, and we are going to give some random noise to the generator, and this random noise is going to be sampled from a normal distribution, just like VAE and standard autoencoder. So this generator is going to generate an image out of this random noise, and we will call that image the fake image. And then we will also have some real images. So we are going to concatenate these fake images and real images in order to create a data set of mixed images. Some of them will be fake, some of them will be real. Then we are going to give that data set as an input to the discriminator in order to let discriminator differentiate between real image and fake image. So the output from this discriminator is going to be either 0 or 1. So 0 means it's fake image, F for fake, and 1 means R or real image. So this is going to give us either 0 or 1, fake or real. So generator is going to convert the low dimensional random sample into an high dimensional image, and discriminator is going to convert that high dimensional image into a single dimensional vector to classify image as fake or real. Now let's talk about the regular training step, because in GANs we are going to create our own training cycle, because training GANs are a bit tricky tasks. So it's really important to understand first the regular training step. So first of all, in regular training step, we perform the forward pass or forward propagation. We pass all the input data from the model, and then we compute the loss between the predicted value and the actual value. and based on that loss we calculate gradients of the model variables. So by variables I mean both the weights and the bias of the model. So find the gradients of the model variables with respect to that loss, and using those gradients update the model variables using an optimizer like Adam or RMS prop or SGD. So these are four basic operations in a regular training step. Now let's talk about the GAN training step. So in a single training cycle, we are going to perform two steps. In step number one, we are going to train our discriminator, and then in step number two, we are going to train our generator, but both of these steps will be in a single training cycle. In step number one, first of all, we are going to pass the random noise from the generator, and this is going to generate some fake images. So we are going to mix those generated fake images with real images, and then we are going to generate labels for that dataset. For all the fake images, we are going to assign 0 label, and for all real images, we are going to assign 1 as a label. And then we are going to pass that the mix of real and fake images from the discriminator, and then train the discriminator on the loss only. So it's very important. We are not going to train the generator in step 1, we are just going to train the discriminator. In step number 2, we are going to train the generator now. Okay, so no discriminator training, we already did it in step number 1. First of all, we are going to freeze the discriminator variables, its weight and bias, because we don't want to update the discriminator variables since we are just training the generator. And in step number 2, we are going to pass a random noise from the generator in order to get some fake images. And then we are just going to pass those generated fake images from the discriminator and assign them label of true image. So although these images will be fake, but we will pretend as if they are real. So we are going to assign label 1. In step number 4, we are going to train the generator based on the loss we will get. So it's really important to understand this concept conceptually, why we need to assign true labels to fake images, because the task of the generator is to generate as much realistic image as he can. So the loss is going to tell the generator how bad your generated image was. It's like comparing the fake image with the real label and finding the distance, how much far apart these two quantities are, and that farness or that loss will tell the generator how you need to cover that distance. I hope you have understood it. Now, let's talk about some of the code. The code is very simple, literally. Since it's a vanilla GAN, that's why we are just using dense layers. In the upcoming videos, we are going to use convolutional layers and other stuff, but leave it to the future now. First of all, the noise shape is going to be 32. You can set it to like 16 or 64 or 128 based on the complexity of your dataset. Since we are going to use MNIST dataset, so 32 is fine. Even though I think 32 is too big for the MNIST, but yeah, let's keep it 32. And then in the dense layer, we are going to use 64 units, then 128 units, then 28 by 28. And finally, we are going to reshape it to 28 by 28 because the MNIST image size is 28 by 28, and we are going to compare this image with the real image. That's why these two image size should match with each other. Now here, as you can see, instead of using ReLU, we have used a SELU as an activation function. So there are two main reasons behind it. One is that SELU is a self-normalizing property. This means it keeps the mean of activation close to 0 and variance close to 1. So that's why we have used here SELU. And the second reason is that ReLU suffers from dying ReLU problem, because if you know about ReLU, its activations are always positive, so it converts all the negative into 0. And when our neurons become 0, and if you find the derivative of 0, you will always get 0. This means the learning gets stops. So that's why ReLU is not suitable for generative part of this GAN. Now let's talk about the discriminator. The discriminator is very simple. First of all, we are going to flatten our input, then pass it through couple of dense layers. In the final dense layer, we will have a single neuron with sigmoid activation function, because this neuron will be either on or off. On in case of real image and off in case of fake image. So that's why sigmoid activation function with a single neuron. Obviously you can use here two neurons, but then you need to change the activation function from sigmoid to softmax, and also the loss function from binary cross entropy to categorical cross entropy or sparse categorical cross entropy. And again, same reason why we have used here celu. Now in the GAN class, we are going to combine our generator and discriminator. So we are going to pass an object of generator and object of discriminator to this class, and then we will initialize it and pass our images from generator as well as discriminator. And this is the final slide of this video. Okay, so this is the training step. Although I have skipped some of the details, but in general this is the core of the training cycle. First of all, we are going to generate some noise, and we will pass that noise to generator first, and then generator is going to generate some fake images for us. We are going to concatenate fake images with some real images. So this is going to be my mixed images data set, and then I need to create labels for this mixed images data set, because in this data set, first of all, I'll have fake images and then I'll have real images. That's why for the fake images I'll use the label 0, and for real images I'll use the label 1. And why this batch size? Because these fake images will be in batches, like we will keep it to 32. That's why these fake images will be 32, then comma, then another 32 real images. So in total we will have 64 images in this mixed images. So that's why I'm multiplying this 0 with this batch size, so that the labels will be 64 as well. First 32 will be 0, last 32 will be 1. Then I'm going to set the discriminator.trainable to true, because in the first step we want to train this discriminator, and then I'll say discriminator.train on batch. I'll provide my mixed images and I'll provide my discriminator label. So it is going to train my discriminator, so not the generator, just discriminator. Phase number 2, we are going to train the generator now. So in order to train the generator, first of all I need to do is to put this discriminator.trainable to false. So it's very important. We don't want to update the weights of the discriminator, otherwise our model isn't going to learn any kind of useful information. And then we need to generate labels for the generator. So here I'm going to generate 1 for my fake images. We have discussed the reason in the previous slides. So just generate 1 32 times, and then say GAN.train on batch. We need to provide the noise and the generator labels. Now why here GAN, not the generator? Because we are going to train generator based on the loss of the discriminator. So here, as you can see in the previous slide, we have grouped the generator and discriminator inside GAN. So the output from GAN will be 0 or 1, and based on that 0 and 1 we are going to just train the self.generator, because we have already put the trainable to false in case of discriminator. So even though our gradients will move through the discriminator, but it is not going to update its weight, because the trainable argument is put to false. So that's why we are using here GAN. I hope this is going to make sense, and in the next video we are going to write our code for GAN, and I'll see you there. Bye bye.